So this will be our last video for section 1.2, and in this video we're going to deal with our first real application problem. And this one is all about mixing tank problems. Sometimes this is referred to just as a mixture problem, and in this technique we're going to be using input-output analysis. And that'll make sense here in a second. So right away at the start, it says suppose that we have a 100-gallon vat that contains sugar water, and that's going to be made into soft drinks. And the sugar water containing 5 tablespoons of sugar per gallon enters the vat through a pipe at a rate of 2 gallons per minute. So these two rates kind of collectively have to do with the input. So if you want to think of it that way, we've got 5 tablespoons per gallon and 2 gallons per minute. That's our input. And then the next sentence says, okay, sugar water containing 10 tablespoons of sugar per gallon enters the vat through a second pipe at a rate of 1 gallon per minute. So we've got another input here. So I'll do this. At 1 gallon per minute. This is another input. And all this is headed into the tank, and sugar water leaves the vat through a third pipe at a rate of 3 gallons per minute. So that's all they give us is 3 gallons per minute, but that represents what we know about our output. So we have 2 inputs and 1 output. And down here at the bottom you'll notice a diagram, just a really rough kind of picture of some big tank. And you've got your output here. And on the other side, you have your input. And we had 2 types of input, if you remember. We had the 5 tablespoons and 2 gallons per minute. This is our green input. And the other one was our blue input, 10 tablespoons per gallon at 1 gallon per minute. Now, a couple things you'll notice about this is that if we have tablespoons per gallon and gallons per minute, what would happen if we multiplied those 2 numbers? Well, I mean, 5 times 2 is 10, but what would the units be? Think about that for a second. Tablespoons per gallon times gallons per minute. You'd have tablespoons per minute. The inputs over here, you could think of as both of them being in how much sugar per minute is going into the tank. But on the other side, we don't have the luxury of tablespoons. We don't know how much is leaving the tank. So part A up here says determine a differential equation for the amount of sugar A of t. So the amount of sugar is going to have units of tablespoons, right? Because that's it. That's all we have. It's not pounds. It's not, inches. That's the amount. And it's not gallons because that's the mixture. What we want is how much sugar. Not how much sugar water, but actually how much sugar is in the vat. So I need to come up with an equation that's going to relate or come up with a way for me to solve for A of t. So determine a differential equation. That means it's going to have to be dt of A of t equals some stuff. That's what we're looking for, where A is in tablespoons of sugar. So that's part A. And then part B says, okay, once you've come up with an equation, you should be able to solve it, and we should be able to come up with something. So notice, presuming that there was originally 1,000 tablespoons in the solution. So notice the language. Originally, 1,000 tablespoons of sugar. This is my initial condition. They're actually giving you the initial condition right there. And then it's asking for how much do we have at, 50 minutes. So this, how much sugar is present after 50 minutes. This is saying, what is A of 50? where A, remember, is the amount of sugar. So we need to come up with an equation that we can solve for A so that we can then plug in 50 minutes and come up with an answer there. So there's a lot going on for this problem. And this diagram right here is really going to help us thinking about inputs and outputs. And this guy right here, this thing right here, is referred to as an input-output diagram. And so what we want to be able to do is turn that diagram into an equation. And so that's what I'm going to do. I'm going to try to do this by kind of scooching my paper down, so scooching the next page down so that we can see. Boop. Oh, this is going to be tough. So that we can see we've got A of t is the amount of sugar in tablespoons in the tank at any time. What I want to do is turn this equation, or excuse me, this diagram into an equation here. So it's going to have inputs and outputs, but it's really relating these two things. It's really saying the rate of change of the amount of sugar. So the equation that we're going to have, I'm going to scoot this off to the side here, the equation that we're going to have, that we're going to use, is the rate of change of the amount of sugar is going to be equal to our inputs minus our outputs. Specifically, this is saying the rate of change of the amount of sugar in the tank is equal to how much sugar is coming in, so sugar inputs, and sugar outputs. So now it's really just a matter of kind of making sure that things work. Now, it's worth noting that when I'm looking at the units for this, this thing is going to have units of tablespoons per minute. That means that these have to have units of tablespoons per minute. Must be in tablespoons per minute. And this thing must be in tablespoons per minute. And the reason for that is because each term in an equation has to have the same units. We don't have a choice. So now I'm going to throw the numbers and the units in that I know for certain. And so from the previous page, let me make sure I do this right with the color coding here. The first input that we had was the green input. And so we're going to have dA dt equals, then on this side my sugar inputs were the green one, which was 5 tablespoons per gallon times 2 gallons per minute. That was my green input. And so notice what happens to the units. If I do this right, the gallons cancel with gallons and I'm left with tablespoons per minute. The next input, gosh, I hope I have enough space on my page for this. The next input was, my other one was 10 tablespoons per gallon. I'm just going to abbreviate gallon to leave myself some space here, times 1 gallon per minute. That was my other input, and sure enough, the gallons cancel again, leaving me with tablespoons per minute. So these two have the same units as what I expect. The last little bit is, oh, this would be plus here, and then minus my output. And if I remember correctly, I used red for the output, so I'll continue using that. The outputs, the only thing we know for certain is we had 3 gallons per minute. But gallons per minute doesn't match with tablespoons per minute. I need to multiply this by something. And the units tell me what I need to multiply it by. I have to multiply this by some kind of tablespoons over gallons. But the question is, what? What goes there? What value do I put there? And what this is really saying is, how much is coming out of the tank at any given time? Well, remember, the tank, let me pull my diagram back. The tank is mixing things up and it's spitting out sugar water. And the sugar water that's coming out of here is actually coming out of here as an amount of sugar per amount of liquid, right? I'm just going to write this as per gallon of liquid. So there's an amount of sugar in the tank at any given moment per how many gallons of mixture there are, and that's how I can figure out how much is coming out. The trouble, of course, is how much is in there. Well, if you have 2 gallons per minute plus 1 gallon per minute going in, so a total of 3 gallons of liquid per minute going in and 3 gallons of liquid per minute going out, there's no net change in the amount of liquid in the tank. So this is really just A of t divided by how big is the tank? Well, it's 100. And this is important. This little blurb right here at the end. This is the amount of sugar. Say how much sugar. And this is a constant volume. Right? It's 100 gallons, and there's an amount of sugar. It's equal to whatever A is, right? It's changing over time. So as time goes by, maybe it's gaining sugar, maybe it's losing sugar. We don't know. But this last little bit right here, if we play our cards right, sure enough, we get our gallons and our gallons to cancel, and all 3 terms are now, or all 4 terms of the equation, are in the same units. Now let me write this out in all its glorious detail without the units, and you'll see this equation is really not that scary. It's dA dt equals, the units I don't care about anymore because I know they work. 5 times 2 is 10, plus 10 minus 3 over 100 times A. So after all is said and done, we have a differential equation, dA dt, that is equal to 20 minus 3 over 100 times A. Or A of t, if you want to think of it that way. Now the question is this separable? Is this a separable differential equation? You might think, oh, it's got 2 terms, so it's not separable. But remember, I can think of this whole thing as a function of A, right? Because there's no t in there. So if I do that times 1, this thing is a separable differential equation. We can use separable or separation of variables. So now I say we can use separation of variables, but we could also just use maple. So what I'm going to do is I will kind of write out what this is going to look like if you did a separation of variables method. You divide both sides by that, and you'd have the integral of dA over 20 minus 3 over 100 times A equals the integral of dt. Now the left-hand side, this integral looks terrible. It's really not that bad. This is just if we do a u substitution and say u equals 20 minus 3 over 100a, and then you find out that du is equal to negative 3 over 100 dA. And so multiplying, you can say dA is equal to negative 100 over 3 du. And a little bit of, monkeying around here, you wind up with negative 100 over 3 times the integral of du over u equals the integral of dt. This side's not too tough. That's just the natural log. I'm going to group my constants together on the other side. I'll call this C1. Now remember, that thing inside there is actually not u, it's this thing right here. So I got to multiply both sides by this negative 100 over 3, or excuse me, divide both sides by that, and then exponentiate. And when we do that, we wind up with 20 minus 3 over 100 times a, that's the same thing as u, is equal to, when I do all the little bit of work here, a little bit of algebra, I wind up with on the other side e to the power negative 3 over 100 times t plus a second constant, which is c2 is just c1 divided by this guy right here. So after a little bit of effort, we can solve this thing for a, and we wind up with a of t equals some new constant c3, it's coming from the upstairs here, times e to the negative 3 over 100 times t, that's all upstairs, plus some extra constant sitting there, right? This 2,000 over 3 is what it turns out to be. Now this is the general solution. If I want to find the particular solution, we can use our initial condition. We'll get to that in a second. I just want to show you, I wanted to show you that you can solve this thing by hand. It's not the end of the world. It's kind of a pain. But if you hop into Maple, you can actually take a look at how to solve this thing in Maple in one fell swoop. We can do it both as a desolve and find the general solution. I'm just going to type in my differential equation, a of t, comma t, and my equation was, what was it, 20 minus 3 over 100 times a of t. Oops, a of t. Now this is Maple solving it, and it should look exactly like what I got. Sure enough, it does. Yay! But we can also have Maple do not just the desolve, we can have Maple do the solution in one fell swoop. And let me type in what that code looks like. I'm just going to copy and paste because I'm lazy. But if I do comma, oh sorry, I have to put extra brackets, curly brackets around this, because I'm having Maple do kind of the initial value problem all in one fell swoop here. So I'm giving it my differential equation, comma, my initial condition. And if you remember, we said that our initial condition was a of 0 equals, we started with 1,000 tablespoons of sugar. That was our initial amount. And so the only difference between this code up here and this code down here is I have those extra curly brackets and an initial condition. And sure enough, Maple says, I can do that. And notice, the only difference, it's still got 2,000 over 3, it's still got e to the negative 3t over 100, but now I know that c1 is equal to 1,000 over 3. So on my paper, I know that how part B works, right? I know how to find my initial value solution here. So I'm going to say all of this up here, this was all part A. All this, way at the start, was all part A. And now I can do part B and say, I know that A of 0 equals 1,000 tablespoons. That was my initial condition. And I can use that to find out that C3 in my equation down here, the C3 right there, is actually equal to 1,000 over 3. Now I could do that just by subbing in the value for A of 0 is 1,000, T equals 0, and then calculate it that way. But Maple did it for me, and so I'm not going to complain. So that means that my particular solution after all is said and done is A of t equals, was it 1,000 over 3 times e to the minus 3 over 100 times t plus 2,000 over 3. But that, of course, doesn't solve the problem because part B says make a prediction. So I can ask, and I'm going to ask Maple to do this for me, what is A of 50? And I'm just going to ask for it approximate out to a couple of decimal places because the exact answer isn't going to be terribly useful for me. So if I step back over into Maple and say, hey, Maple, now that I've got A of t right here, I'm going to evaluate that, and I'm going to evaluate the right-hand side of this equation. The right-hand side of number 10, so Control L for which label. I want number 10. So what's the right-hand side of number 10 evaluated when t equals, and if I type in 50 with no decimal, it'll give me the exact answer. Oh, whoops, I forgot my delimiter there. Which, of course, that's the exact answer, but it's not terribly useful. But if instead I type in 50.0, Maple says, oh, okay, you want decimals. It turns out to be about 741.04 out to 2 decimal places, and we're talking about the number of tablespoons of sugar. So this turns out to be about 741.04 tablespoons of sugar. That's how much is in the tank at 50 minutes. Now, we were able to do all of that, but we could just as easily in Maple have said, you know what, I've got the particular solution, so I don't even need to know at 50 seconds. Instead of evaluating the right-hand side, I could tell Maple, hey, can you plot the right-hand side of number 10? Close that. Where t is, let's go from 0 to 60 seconds, or 60 minutes. Maple says, sure, no problem, I can do that. And we actually get a sense of what's going on in the tank. The amount of sugar here, and by the way, the vertical axis, we can change, we can make it go A equals, I don't know, 0 to, looks like we need to go up to 1,000, our initial amount. And I'm going to actually add a label. I'm going to call a title of this graph. And for title, you put it in quotes. And so I'll say amount of sugar over time. That's going to be my title of my graph. And so Maple says, sure, no problem. This is what it looks like. Notice I changed the vertical axis settings so that I'm going from 0 to 1,000. And it looks like it's a nice steady decay. It looks like it's kind of decaying, but it's slowing down. The question is, what happens if I let it go not to 60 seconds or 60 minutes? What happens if I let it go to 600 minutes? And you see something that starts to make you wonder, what's going on with this graph? It looks like it's headed towards some kind of a equilibrium solution. Quick, back to the equation. Take a look at that. My particular solution, as t approaches infinity, what happens to this term right here? As t gets bigger and bigger and bigger, it's e to the negative infinity, which is 0 as t approaches infinity. So this whole term just goes away, and you're left with 2,000 over 3. 2,000 over 3 is ballpark 660-some, 667. Sure enough, that's about where it's headed, right here. So the plot allows us to see that equilibrium solution that we might have missed in the equation. But the equation itself allows us to make a specific prediction. That gets us to the end of this problem and the end of the section. You'll notice at the very end, the last page, there's an example from page 36 that I want you to tackle. Give that a try. I will write down the solution on this paper and I will post it for you to take a look at later. But that gets us to the end of the videos for section 1.2.